Okay, folks, welcome. I would like you to meet a buddy of mine from the old days. We both worked at NASA and the Lunar Planetary Institute in Houston, and he's visiting South Africa at UCT, where he's working with Petrus LaRue on some stuff in the Andes. He may talk about some of that today, I'm not sure. But this guy, Shanaka de Silva, very interesting background. Born in Sri Lanka, went to boarding school there for some time. His parents dragged him off to London. I don't know what they did there, probably educated you further. And then they moved to Africa, they moved to Nigeria for a while, and then back to England, where he eventually was educated at the University of Southampton, wherever that is. And then his PhD comes from the Open University in Milton Keynes, wherever that is.
You don't need to know.
We don't need to know.
Very boring.
I've never been there.
Lots of roundabouts.
Lots of what?
Roundabouts. Block system.
Lots of roundabouts.
Yes.
And
Concrete cows, yes, don't forget the concrete cows.
Which is amazing to me. I never heard about that.
Anyway, let's move on here. Let's move on.
After his PhD, he came to Houston to work with his former supervisor, a guy called Peter Francis, another good buddy of mine who is now, unfortunately, gone to heaven at a very young age, but a volcanologist extraordinaire. And so I met Sean in Houston. I think that must have been 87. He stayed there, I don't know how long, but I left at 98 to come here. And then after Houston, I think he went to take an academic job at Indiana State and stayed there for a number of years, and now at Oregon State, where he presently works. And he is going to talk to us about that subject that you see there. And you're all welcome to chit-chat with him after the talk, if you like. So I give it to you. Have I forgotten something?
No, this is plenty. Thank you. Thanks a lot, Lou.
Sure.
As you know, with Lou, you never quite expect what he's going to say in the introduction. So I think my nervousness is gone now. So you'll notice that I flipped the title a little bit because I'm primarily a volcanologist. So I start at the surface and then kind of sort of figure things out underneath the surface. So that's the way I'm going to structure this talk. And I'm really, what I want to do is sort of tell you from a volcanology perspective what we can infer about the continental crust underneath these big volcanic systems that we call supervolcanoes. So I'm going to start with supervolcano. And some of you may be familiar with this term. It's a sort of a hyperbolic term a little bit, and it sort of engenders all kinds of hyperbolic titles and things like that. But there are some quite good academic works as well associated with, I've lost the...
it's on the left side of
this one? This is yours, I think. I'll find it. Anyway. So there's it's a topic that is very popular in the sort of volcanology community because there are some quite active ones. Here we are, quite active ones, and in particular, Yellowstone is in the northwest United States, and is considered a potentially active supervolcano, and the possibility of super eruptions from such volcanoes causes lots of concern, and governments have policies in place and so on what we would do in the eventuality of one of these eruptions. And there's all kinds of questions about timing and so on of how these volcanoes work, and I'm going to talk a little bit about how we figure out the operations of supervolcanoes and what they tell us about the interior of the Earth. This is a scale that we use. This is called the Volcanic Explosivity Index, VEI. and it's a logarithmic scale that essentially categorizes or classifies volcanic eruptions in terms of volume. And just to give you some idea, sort of a familiar one that most people may know is the 1980 eruption of Mount St. Helens. That was a 1 cubic kilometer eruption, and that's a VEI 5. In 1991, there was the eruption of Mount Pinatubo in the Philippines. That was about 10 cubic kilometers, and that's a VEI 6. The biggest eruption in history that we know, human history, is the 1812 eruption of Tambora, which was in the sort of less than 100 cubic kilometer range, and that's considered a VEI 7. The things that I'm going to talk about are 10 times larger than that, and that's this big thing here. And so Yellowstone, 600,000 years ago, these are classified as a VEI 8, and that's where the term sort of supervolcano or super eruption comes from. So how big are these eruptions? This is a isopac map of ash from the 74,000 year eruption of Lake Toba. That's a big supervolcano, this little blue dot here. And these are basically thicknesses of ash from that. And based on this, you can calculate the volume of this eruption. And the latest estimate is that this eruption erupted about 5,300 cubic kilometers of magma. And this all came out within a few weeks. Okay, so these are not huge volumes when compared to flood basalts, but they erupted at a much, much more catastrophic rate than flood basalt. So if you think about 5,300 cubic kilometers, that's a very large volume. It's difficult to sort of scale these things for people, but if you think about Mount St. Helens was a VEI 5. These are VEI 8, so 1,000 times larger than Mount St. Helens. 1,000 cubic kilometers of deposit, 450 cubic kilometers of magma, that's the minimum. So Toba was like a 10 times that, which puts it actually at a VEI 9. And a super eruption is about at least 1,000 times bigger than Mount St. Helens. So what this slide here is depicting is 1,000 Mount St. Helens erupting at the same time for about a week, and that would be the extent of a super eruption. Okay, so if we look at the mark that's left, these are sort of typical calderas that are produced by explosive eruption. Crater Lake was a big eruption about 7,000 years ago in Oregon. This is an 8-kilometer diameter caldera. It's a very pretty place. This is Santorini. This was about 100 cubic kilometer eruption, and these are other ones that are well known in the literature. Okay, so these are quite large. The largest one here is this one. This is about 20 kilometers in diameter. And so here's Crater Lake, 8 to 10 kilometers. Taupo, the one that I just showed you, is 35 kilometers. Supervolcanoes are this size here. So if you put Johannesburg on one end, Pretoria would be at the other end. It's about 90 kilometers to Pretoria. Okay, so that's about, sorry, how far is it?
It's 50 to Pretoria.
Oh, okay, so Pretoria will be about halfway down here. So the entire region from Johannesburg to twice the distance to Pretoria would be essentially a big collapsed basin resulting from this eruption. Okay, and then the area out to about 100 kilometers surrounding that is going to be covered in ash deposits up to 50 meters thick. So essentially everything is sort of buried there. So what we're particularly interested in is what can we use from the products of these eruptions to tell us about what's going on underneath this big caldera system here. Okay, and to give you an idea, these would be typical sort of volcanoes that you'd see in a volcanic arc, and you can see that the collapse area that produces the caldera basin is many, many times the size of these volcanoes. And what we assume is that we can look at these deposits and infer what's going on underneath the surface. Okay, so most of my work has been done in the Central Andes, and this is one of the systems that we studied there. This is the Guache caldera in southwest Bolivia. These are just some field photographs to give you some ideas of what this looks like. It's a high altitude plateau, hyperarid, and these ash deposits here basically blanket the terrain. Here's the caldera here. I don't know if you can see the blue lines here. Those are the collapsed scarps of the caldera, and it's about 60 kilometers from east to west. And then the deposits from that go out as far as 70 kilometers to the north and about 50 kilometers to the south. And these deposits vary from about 2 kilometers thickness in the caldera to about 15 to 20 meters thick in the distal reaches. So very large volumes of these ash deposits. And just to give you, again, just some idea of what the terrain looks like, there are many such eruptions, and they produce this sort of plateau of ignimbrites that the modern volcanoes of the arc are built on. There's about 2 kilometers thickness of these ignimbrites. And most of my work to start off with was essentially mapping these out and age dating them to try and figure out the extents of these eruptions here. And again, what we're trying to do is once we've figured out the stratigraphy and the volcanic history, then we can start sort of questioning these deposits to try and say something about what's going on underneath. Okay, so we use a sort of a range of different approaches to try and get at the questions that we're interested in. It all starts up here with the field work. We use paleomagnetism to try and figure out directions of transport and also to help with understanding some of the timing. Remote sensing is important because this is a very large area, and it's actually a great area to use remote sensing for mapping these deposits. And then, various different geochronology techniques, bulk geochemistry, micropetrology, and then we combine that with geophysics and some numerical modeling to try and figure out what's going on in the deep crust that we can't see. So just a quick summary of the geochemistry. There's over 15,000 cubic kilometers of magma represented in the deposits on the surface. Okay, and most of these, this is a histogram of relative volume and composition. Don't know if you can see this, but about 85% of that volume is high potassium dacite. So between about 67 to 69% silica. So a very narrow range in silica content. There are some rhyolites, but they're volumetrically very minor. And then there are some andesites, which are also volumetrically very minor. When you look at the composition of these ignimbrites compared to the continental crust in red here, we can see that there's a strong similarity between what's erupted and what's typical continental crust, upper crust in this case here. If we look at isotopic space here, this is strontium 8786 versus neodymium 143, 144. We can use this to do some mass balance between mantle compositions and crustal basement compositions, and look at the relative amounts of mantle to crust in the magmas that we're looking at. And what we find is that there has to be at least 50% crust mixed into a typical mantle end member in order to produce the compositions of these ignimbrites here. So there's a very large scale, what we call assimilation, fractional crystallization going on as mantle magmas enter into the crust. And what this is a crystal size distribution diagram. And it's essentially showing you that these are very coarse-grained porphyritic magmas. They have up to 50% phenocrysts in them. And if you think about the rheology of these things, that's almost at the critical limit at which you can erupt rhyolitic magmas. Okay, so these are compositionally very limited in range. They look like granodiorites, or the upper continental crust. They are the product of large-scale mixing of crust and mantle, and they are extremely crystal rich. In fact, we call them mushy magmas. So one of the things we want to try and figure out is how long were these magmas assembling before they erupted. And a favorite tool for that is the crystal zircon, or the mineral zircon. And zircon has the property that you can age date it, and its chemistry also tells you about the processes involved in its production. So what we do is we analyze these 100 micron scale bars here, and we analyze sort of 20 to 30 micron scale spots, and we can get the age of those spots, and we can also get the trace element geochemistry of those spots. And we need the trace elements to try and figure out the temperature at which these zircons formed at. Okay, so we've done a large amount of this. And one of the things that we do is we look at a caldera complex like this, a supervolcano like this. This is the Pastos Grandes caldera here. This is a map. The different colors represent the distribution of deposits at different times of eruption. And we're going to look particularly at the blue deposits, these ignimbrites, which were erupted 2.89 million years ago. And when we look at the zircons from those, we find that the zircons define an age range from about 4 million years down to the eruption age at 2.89 million years. Now, there are subsequent eruptions immediately after the caldera formed, which we think represents the remnant magma from that caldera forming eruption. And those define an age range going from about 3.5 to about 2 million years. And then there are granite clasts, which came up in a later eruption, which then define the age of the pluton that solidified from that magma. So we argue that we can go from the pre-eruption assembly of the magma that erupted in this caldera to the point that it solidified, and the age range is about 1.1 million years. So the minimum age for this magma that erupted from this caldera is that it took about 1 million years to accumulate to a volume of about 1,400 cubic kilometers. So it's gradually built up over time, and then there's a catastrophic eruption, and then it's solidified. So this tells us that underneath this caldera, there had to be a large pluton growing underneath there before it was erupted, and a large amount of that magma was left unerupted. We can look at the temperature of saturation of those zircons, and the majority of those zircons come in at about 700 to 750 degrees centigrade, and that temperature seems to have been consistent over a very long period of time. So this is a big volume of magma that is sort of buffered in terms of its temperature. And then you can make some assumptions about the conditions at which zircon crystallizes, and use the trace element geochemistry and couple that with thermal models to figure out how much heat needs to be brought into the system, heat and mass that needs to be brought into the system to maintain that temperature range over the required time frame. And it ends up being a very significant volume of magma. And we find that the intrusive to extrusive ratio locally can be as high as 35 to 1 to 75 to 1, depending on the what's going on at the surface. Okay, so these volcanoes can be thought of as places where magma is coming out, but there's much more magma sitting underneath. So the other thing we want to know is, well, where is this happening? At what depth? So there's several ways we can get at this. One of the more popular ways is to look at these little melt inclusions in quartzes, because quartz is a fairly stable mineral. And if you look at the ratio of water to carbon dioxide in these melt inclusions, we can define saturation pressures. And these are contours of 200 megapascals, 100 megapascals. And you can see that most of the pressures that are defined are in that sort of 150 to 100. So this is about 3 kilometers to 2 kilometers. Similarly, this is another study that was done on one of the other systems, and then here as well. So we think that these magmas, the tops of them, were being stored at around 2-3 kilometers on downwards, and that's what gets erupted. You can also do experiments. These are some experiments that students of mine did on the compositions that have been erupted, and we know the mineralogy, and we can recreate the conditions under which that mineralogy would be stable. And you can see here, in this case, in this system, we're at around 50 megapascals to 100 megapascals at about 800 degrees centigrade. And in this one here, we should be just lower than the orthopyroxene out, because we don't have orthopyroxene in most of these. So we're in this range here. And so the experimental data agrees with the melt inclusion data, suggesting that things are happening up in the uppermost crust. Okay, so then we take that information and various other bits of information about the volcanology and the petrology, and we sort of produce diagrams like this that essentially summarize the evolution of the system from before the eruption, the building of the magma system, up to the initial eruption, during the major part of the eruption, and then what happened after the major eruption has happened. And the point here is that we use various different tools to try and come up with this information. You can see here that we can sort of place depth constraints on where this is happening. We know the volumes that were erupted, so we can sort of start saying something about what's happening in the uppermost crust here. Okay, so we're beginning to build a picture of what's going on in this area here. All right, so what I've told you so far is that these super eruptions require large volumes of magma, thousands of cubic kilometers of mobile magma to be available pre-eruption. Most of these magmas are quite mushy. They're very crystal rich. They're not quite plutons, but they're plutons with a lot of melt in them, and they're barely eruptible. They have long lifetimes, hundreds of thousands of years to a million years to build up that volume. They are stored at around 3 to 8 kilometers. And what these calderas or these supervolcanoes are doing is they're kind of acting like valves that are modulating the pressure history inside those plutons. So I'm going to switch now to a sort of slightly broader perspective. I was talking about some of these centers in the Andes, just to give you some background to the region that I'm talking about. The Andes is probably the archetypal convergent margin on Earth. There are 4 volcanic zones produced by subduction underneath the subduction of the oceanic Nazca Plate underneath the continental South America. The Nazca Plate is moving to the east. South America is moving to the west. And the 4 volcanic zones are separated by zones of no volcanism. And the reason for that is that there is a change in the angle of subduction. This is sort of basic plate tectonics, that the places where there are no active volcanoes is where the subduction zone is shallow. The places where you do find magmatism, like the central volcanic zone or the southern volcanic zone, the subduction angle is deep. And you're creating magmas here by hydrating the asthenosphere, and that magma comes up as volcanoes. So the angle of subduction is important. So the other thing that you see is this is contours of crustal thickness. And I don't know if you can see here, but crustal thicknesses in the central Andes are much greater than crustal thicknesses in the other parts of the Andes. And actually the thickness of the crust gets to about 80 kilometers. And you'll see that this is the area where the calderas that I was talking about is. Okay, so 80 kilometers of continental crust. Typical continental crust is, on average, 30. Lou likes 35. I like 50 in the Andes, but we can argue about that. So one of the results of this crustal thickening, kind of like the Himalayas, is that you have very high surface elevations here in the central Andes. In fact, the plateau in the central Andes is the second highest plateau in the world, next to the Himalayan plateau, and this 4 kilometer average elevation of the plateau is largely thought to be due to crustal thickening, doubling of the thickness of the crust. But we'll talk about that in a minute. So one of the things that's not well known about the Andes is it's actually a silicic large igneous province. Most of the work that's done on the Andes looks at the young volcanoes and that define the active volcanic arc. But those young volcanoes are built on a 14-degree latitude extending silicic igneous, large igneous province. All these different orangey colors and yellow colors are distributions of silicic volcanic deposits that form this extensive plateau. And one of the things that we can see going from the north to the south is that there's an age progression. And when we look at the flux, the rate of magma production associated with the this silicic large igneous province, it's much higher than what happens in the background forming the magmatic arc. So we call these flare-ups. This is a time when the Andean arc was producing magmas at a much greater rate than under normal steady state conditions, and I'll explain that a bit more a bit later. So we're going to go and look at this particular area here, this portion of the large igneous province, and that represents a group of calderas. I don't know if you can see these sort of yellow outlines, but each of these are individual calderas, and they're all sort of linked spatially and temporally. And so this is a detailed map of that. There are at least 4 major calderas here and several smaller ones. The different colors represent the distribution of deposits from them. This black line separates the country of Chile from Bolivia, from Argentina. And what we've done is trying to sort of understand each of these calderas, the volumes that I just talked about, and what's going on under each of these big calderas here. So if you can imagine from what I just told you, under each of these is a pluton, and each eruption represents a pluton which has been disrupted. So there's 10 different, no, that's not on here, but there's 10 different super eruptions here. So each of those represents 10 different plutons in here, and as a composite, they form this big composite batholith that sits under this area. Okay, so we used the information that I gave you earlier on how we figure out depths and ages and longevity and things like that. And then we looked at the sort of distribution, age distribution throughout this whole region. We started off with argon-argon geochemistry and geochronology. And argon-argon gives you the eruption ages. And using that information, we can see that there were eruptions of different volume. This is volume here, this is age here, and each of these lines represents a major eruption. And then these are the distributions of this. So you can see this sort of patchwork sort of building up of, you can get a sense of maybe you're sort of producing a large sort of igneous mass underneath this, this area here. So when we looked at the zircons from these, remember I told you that zircons give you an idea of the sort of time it took to build these before eruption. The eruption ages are in the black line, and the distance, this is age along here, to the right of the line represents the time it took for that magma to build up prior to eruption. Okay, so in each of these cases, each of these eruptions had magmas being emplaced prior to eruption, several 100,000 years prior to eruption. They erupt, and then either a new system grows or the system dies. So we can use that information to try and understand how each of these calderas evolves over time. And this is one of these calderas, and there's been 3 major eruptions and several small eruptions, and these are the zircon and potassium argon ages, argon ages of those eruptions. The point here is that you can see that the ages get younger and younger because the eruptions get younger and younger. And what we also see is that subsequent eruptions often contain zircons from the previous eruption. So they're cannibalizing the plutons that were left from the previous eruption. So we see this cyclicity in these calderas that are telling you that magmas are brought in, they grow and they erupt, magma's left over, the next magma comes in, it cannibalizes some of that pre-existing magma, another eruption happens. So these calderas represent sort of periodically erupting valves from these growing plutons underneath. So if we put the zircon records together with the eruption history, what we can then define is where were the magmas in the upper crust being emplaced over time. And so we see sort of 4 different stages of eruptions and the buildups to eruptions. So these would be the plutons, and then the eruption, the plutons, the eruption, and so on. So stage 1, the earliest stage of this region, are these green dots. And you can see that they're quite small and they're distributed quite broadly. Okay, and those represent eruptions out here. Then we get a pulse of eruptions at 8 million years, which is this one and this one out here. And then when we get into the 5.6 and the 4 million year pulse, we can see that those are much larger volumes and they're more centralized. And so what you can imagine is that as magmas are coming into the upper crust here, the crust is getting warmed up, and the central part of the region is getting much more ductile. You can emplace more and more magmas into there, and you can grow larger and larger magmas before they erupt. So the largest volume eruptions, there are 3 eruptions here at 4 million years, which are in the multi-thousand cubic kilometer range, and those are found right in the center here. So these will be the largest plutons, and the smaller plutons are out here. So we're looking at a slice, if you like, kind of a X-ray slice at about 3 kilometers to 5 kilometers depth underneath the calderas here. Okay, so this is this idea that you've got these plutons gradually forming a sort of a collection of plutons that define a batholith underneath this region. Okay, so from the geochronology, we can say that these calderas are long-lived magmatic locations. They're nested. That means there's several eruptions from the same caldera at different times. When you sort of look at them as a group, they map out the development of a large upper crustal batholith. And the batholith is incrementally constructed over time. Remember, we have those 4 pulses, and so this is incrementally constructing over time. And the volumes of plutons increase over time and become more centrally focused. So we still really don't know what's going on at depths below about 8 kilometers, because that's where petrology gets you. So this is where we can sort of start using some models and some experiments with geophysics to really try and delve deeper into the crust beneath these upper crustal systems. It's a very active area. We know that there must be hot magma underneath there because you have these big geothermal systems in the calderas, even though the last eruption was 1 million years ago. So we know that there's heat underneath these calderas here. Okay, so just again, think about scale here. Here's 75 kilometers, so more than the distance from Johannesburg to Pretoria. This is about 350 kilometers by about 200 kilometers. So roughly about the footprint of the exposed part of the bushveld, is that right? Somewhere around there, maybe in that order. Okay, so if you can imagine, underneath here is some kind of big intrusive complex. We're trying to sort of image that intrusive complex. So here are the calderas. This is gravity data, and this is a residual gravity map. And what it shows is, so here's the scale here in milligauss. The area of the calderas sits right above the lowest gravity, residual gravity anomaly in the area. So there's a lot of low density material sitting underneath, as we predicted from the petrology. Okay, and we get down to about 80 milligauss in terms of the residual gravity there. There were some magnetotelluric experiments done by Martin Unsworth and his group. This was part of a multinational and multi-institutional project that we were part of. And what the magnetotellurics, so for those of you that aren't familiar with that, it's essentially a measure of conductivity. So fluids and melt will be more conductive than cold solid rock. And the reds are more conductive areas and the blues are less conductive areas. So you can see here is the area of the APVC, the Altiplano Puna volcanic complex that I was just talking about. And there's a big deep zone of conductivity down here, 30 to 50 kilometers. And in more detail here underneath in this particular box here, you can see that from about 15 to 25 kilometers and then on up towards the surface, there are these highly conductive zones here. Okay, so those could be fluids or they could be melt. And then the seismic experiments were really quite revealing. Here again is the area of the calderas, and there were seismic experiments conducted throughout this region. And the region of the calderas is this area up here. This is the modern arc today. And there's a regional low velocity zone underneath the calderas again. And some of the velocities are so low that it's been argued that there is up to 25% partial melt sitting in here. And that goes from about 5 kilometers down to about 30 kilometers. So again, as predicted from the surface geology and the petrology, we should see evidence for what 10 million years of magmatism has done to this crust. And it appears that there is hot, ductile, relatively ductile material sitting underneath this region here. And the scale here, this is shear velocity in kilometers per second. So these are in the 2.5 and lower velocities in here. Okay, so what has been finally imaged is a large igneous intrusion with about 25% melt currently existing. Volume here is over 500,000 cubic kilometers from about 5 kilometers down to about 30 kilometers. Okay, so it's not quite the Bushveld, maybe about half the volume of the Bushveld, but this was produced in 10 million years, we think. And remember, this is an arc environment, not a plume, so we wouldn't expect quite the magma productivity that you'd expect in a sort of plume environment. But this is a significant volume of low velocity material, which is most likely melt, compared to the upper part, which is most likely fluids and saline brines and things like that. Okay, so underneath the calderas, the petrology helps us sort of figure out what's going on just underneath the calderas, the pre-eruption level. But deeper down, it looks like in the most of the upper crust is this big sort of magmatic complex with a large intrusion sitting underneath there. Again, about half the size of the Bushveld, which is a pretty significant volume underneath there. Okay, so the calderas, the Altiplano Puna volcanic complex, sits above one of the largest negative gravity anomalies in South America. The magnetotellurics and the seismic tomography reveals evidence of an extensive partially molten zone from about 5 to 30 kilometers beneath the Altiplano Puna volcanic complex. This is more than 500,000 cubic kilometers, up to 20 to 30% melt today. And this implies intrusive to extrusive ratios of 35 to 1. Okay, so this is much higher than other estimates that people have been using for years based on various different data compilations and so on. And we interpret that big red blob, as kind of the sort of batholith, the mothership batholith that fed the volcanism at the surface for 10 million years. Okay, so if you want to sort of figure out magmatic rates, the time frame over which this was constructed is probably 10 million years or so. So we take that information now and then we try and sort of figure out, well, what does this mean in terms of the entire crust and how subduction works in the Andes and maybe in other places and so on. And we've presented models that arcs work in sort of two different ways. The normal sort of arc mode that you read about in textbooks and so on produces these beautiful composite volcanoes, and you get a chain of them going down, and that represents the subducting slab in what's called steady state mode. It produces magmatism in the asthenosphere. Those magmas come up, and then they produce these volcanoes here. So that will be this case here, where magmas from the mantle come in, they assimilate and fractionate in the lowermost crust, and then they may make it straight up through into a composite volcano with some time in here. During times of these big caldera formations, those are flare-ups, because the rate of magma production is orders of magnitude greater than during steady state magmatism. And so what happens here is that you produce, the same process goes on in the lower crust, but at a much faster rate, but that intrudes magmas at a rate fast enough to build a large upper crustal zone, which in itself is also a zone of assimilation fractional crystallization. We call that upper crustal mash here, and this we think is andesitic to dacitic because we can see some vestiges of this in the erupted material, slightly deeper than what comes out in most of the eruptions. We produce these pre-eruptive magma reservoirs, and these are the things that explode or erupt during these big caldera forming eruptions. And you can model what's going on in these different parts of the system. Stage 1 produces magmas that are, have this particular isotopic composition. It's a baseline isotopic composition for the Central Andes. That then gets further modified to this level, at this level in the crust, and then in the uppermost crust you get further fractionation and assimilation to the final compositions that are erupted. So our view is that a lot of action happens in the upper crust. There are groups that believe that everything that happens in arcs happens down here, and the upper crust is just a place that the magmas pass through. We don't see that, particularly in this sort of big flare-up stage. Everything is happening, or a lot of things are happening up here in the uppermost crust. So there's just one more thing I want to quickly say. We're pumping all this material into the upper crust, right? And remember that the Central Andes has this very high plateau that characterizes the topography of the region. And that plateau is thought to have been produced by doubling of the thickness of the crust as the South American shield was pushed under the upper part of the crust here. So we double the thickness and we produce this high, 4-kilometer high plateau. When we look at the area of calderas, we see there's actually a topographic dome. Here's the area of the calderas here, and here's the anomalous elevation topographic dome associated with those calderas. Okay, and there's about 1 kilometer of excess elevation above the plateau. This again is about the size of the Bushveld complex. So what's producing this excess elevation? Okay, if we look at these are the elevations of the basement. Okay, these black dots, and we can see that the basement is elevated on the plateau compared to the flanks of the plateau. So something has pushed the basement up. And when we look at the impact of the low density material on so we use the buoyancy of that low density material, and we calculate the impact of that on topography, we can argue that the presence of this low density material underneath the calderas is responsible for doming that area into this topographic dome. So some of the elevation is not just purely from tectonics, but also due to magmatic addition into the uppermost part of the crust. Okay, so take-home points. Large calderas or supervolcanoes act like valves. They tap the tops of upper crustal granitic plutons. They're composite features that map out the development of a composite pluton in each individual case. And when you look at them as a group, they're mapping out the development of a sort of a regional batholith. These complexes can be geophysically imaged, and they suggest that these are big zones of upper crustal AFC, assimilation fractional crystallization, that solidify into upper to mid-crustal batholiths. Some of these batholiths are the result of high flux or flare-up mode of arc magmatism. I'm not saying that all granite batholiths are produced in this particular way, but when you look at young volcanic arcs with young volcanic provinces on them, we see lots of evidence for this high flux magmatism that produces large granite batholiths there. Okay, so thank you very much, and I just want to finish with this. You know, this is not all done on my own. There's an awful lot of collaborators involved here. Most important are the grad students that have worked with me over the years. I've sort of condensed 25 years of research into 45 minutes here, and you know, so a lot of thanks goes out to the graduate students that have worked on these kind of problems. So thank you very much.
Questions? And I'll turn the lights on so we can see you. Bryce, let's start with Bryce.
Thank you very much for an interesting presentation. I'm very impressed by these super eruptions, guys, and that with the rate of eruption, let's take Bishop Top. So 600 cubic kilometers in 6 days, if we believe Hillary. So okay, 100 cubic kilometers in a day, just like that. So my problem is that I cannot really understand, how you can produce such great amount of the magma from the zone, marshy zone, which you say, in your case, you are generous, you give 25% of liquid, but for Yellowstone they give 2%, 9% of liquid in the marsh. How you can really separate this tiny amount of liquid and erupting in such a rate, 100 cubic kilometers in a day? What is your vision of it?
Yeah, so there's two issues there. One, you're talking about separating eruptible magma from a mush zone. So you're assuming that the mush zone is not eruptible. How do you separate thousands of cubic kilometers and then erupt them? The pre-eruptive magmas are all eruptible. So they represent magmas that have built up over 1 million years, in this case, and then they are erupted when they reach a particular stage. Okay, so it's not a matter of trying to collect magma together and then erupt it in that short period of time. There's a whole pre-eruptive buildup before you actually erupt them. There are some models that suggest that you have to do this in a very short period of time, but we're dealing with crystal-rich magmas here. So we're not segregating residual liquid from a big mush and then erupting it. We're erupting the top of the mush itself, and that upper part of the mush is eruptible.
So this upper part, there contain huge amount of this totally molten magma.
It's not totally molten, it's 50% crystalline at most, right? So if you can think of a gradient of crystallinity, right, with the crystal content increasing as you go further and further down. We're looking at the part that, only a part of that is eruptible because of the amount of melt that's available.
May I ask you just one? How do you separate this liquid from the mush to build this for many years?
You don't have to separate them because you're erupting the crystals with the mush, with the melt
And
itself.
You said that this is building for many years to form this
Right.
battle part. How you build it? How you separate this liquid?
So if you go from the mid-crust, from the lower part of the system, let's get up here. So this is the mush here. So this is the parent. To get from here to here, there are instabilities in this mush, in this zone here, which operate on a 1 to 2 million year time scale. So that sends mush or residual liquid from this, which is andesitic. That andesitic material then fractionates to produce the magmas that are erupted. So it's an instability in this mush zone here, which is being fed by here. So it's not a question of suddenly collecting 1,000 cubic kilometers and erupting it. Those models, I don't understand those models, but in our case, we think that over time, you build up these eruptible magmas, and then finally you get to a point where they can erupt. Right.
Okay, Robert, I think you have your hand up.
Yes. What actually
stability and it just explodes virtually? Or is there an underlying mantle related or heat related thing that causes these episodic workings of these systems?
Right, so this is a question I get a lot, and so I had a slide prepared for this. So remember I told you that this is a silicic large igneous province. So I just talked about this area here, okay, which is 10 million years to 1 million years. But this type of volcanism has been going on from the north about 25 million years ago down to the south as recently as in the Holocene. And that time transgression tracks this, these black lines are the trace of an aseismic ridge that was in these positions at these times. So as the Nazca Plate is subducting underneath here, you've got this aseismic ridge being gradually moving southwards. So what happens with that ridge is, so where are we here? This is stage 1, yeah. So here's the geometry of the slab with the aseismic ridge on it. You can see that there's no asthenosphere in that location. As the ridge passes through, the volume of asthenosphere increases because the ridge has now passed and there's a space, and asthenosphere can now ingress into that area. And then one of the other thoughts is that the base of the subcontinental mantle lithosphere and lower crust is unstable because it's primarily eclogite and high density, and it peels away through delamination, and that allows this ingress of heat and mass, and that's what drives the high flux event here. So, you know, through time, as this has sort of passed southwards, you've had this process going on that has caused these flare-ups, basically.
Sue, you had, I'm sure, geophysical question.
A little bit. The levels at which the upper crustal chamber and the lower crustal chamber are imaged at, is that controlled? What are the main controls on where those accumulate? So that
Yeah.
from 3 to 20 kilometers, is that based on crustal strength or pressure and temperature, or what are the main controls on where those levels are?
So it depends who you talk to. So the petrologists and volcanologists like phase changes. As you bring magmas up here, you dewater the magmas, and they essentially stall and they crystallize at about 15 kilometers. And so part of this process is simply the fact that you have water-rich magmas, and that the water exsolves out of the magmas, and you essentially stall them, and it crystallizes and forms this big mush in here. It's kept going by heat coming from below, so it doesn't crystallize completely. But there are also some horizontal structures in here, which are probably structural features that must also control some of this as well. And then there's a neutral buoyancy argument, depending on what the composition of these are. We think that these are primarily basaltic andesites coming up from here to here. And when you look at their neutral buoyancy compared to the surrounding crust, this is about where they would stall as well. So some combination of those three things. This one here, that is primarily due to, this is essentially a mantle magmas coming in from the mantle and mixing with the crust, and their density is such that they would pond at the base of the crust here.
Roger.
I'm glad you mentioned tectonics right at the end, because my question is, a lot of these calderas look to be slightly elongated.
Yeah.
And the processes you're describing about the ridge going down, or the what have you, will generate stresses in the crust.
Uh-huh.
And stresses would be essential for allowing the melt to migrate upwards. So is there a link potentially between these things forming during transtensional or extensional events within the overall tectonic system?
I actually have, so I actually think of these things as volcano-tectonic depressions, so they're not purely volcanic features, and part of the reason for that is that we do see, I think, a strong role for tectonic pulsing in particularly controlling several calderas going off in sort of closely spaced time. They're oriented along sort of crustal tectonic trends, and if you think of this area as kind of an uplifting, extending topographic dome, you've got extensional forces on there, and I think that's actually a very important part of how you produce the collapse structures and actually initiate the eruptions. So yeah, I mean, I didn't get into the volcanology of how these calderas work, but they are actually very strongly dependent on the stresses in the upper crust here.
I think the lower crust too might be.
Yeah, but yeah, I mean, it depends whether you think that what's happening in the lower crust gets transferred up to the upper crust or not, and there are people who, argue either way.
Good. I saw your hand.
Given all these requirements, I mean, there's obviously then a limited set of circumstances or areas in which these things can form. So, I mean, you're not going to find them in an island park situation because there's just not the requirements to be met. So, I mean, have you looked anywhere else in the world where similar sorts, even for much older periods of time, for example?
So thick continental crust is important, and not really thick. I mean, you can do it in sort of 40-kilometer thick crust and so on. There are flare-ups or these big caldera events in Sumatra, in New Zealand, at Yellowstone, which is a plume setting. So the main control there appears to be continental crust, because you need to be able to produce the volume of silicic magmas. And you can't do it in thin crust because you simply can't bring enough basalt in to produce. You need to assimilate lots of continental crust. So that's the primary thing, and then you need that mechanism for elevating the heat flux into the base of that crust.
Musa, I saw your hand. Before I leave.
It's more of a comment. I think you've got beautiful data from hydrology, geochemistry, supervolcanoes, gravity, metatellurics. You missed deep reflection seismics to answer some of them.
We don't, yeah, so, I'm not a geophysicist. I know a lot of geophysicists, and so, I trust them to use what is needed to answer the questions that we need. My impression is that they prefer the refraction work and the receiver function data to the reflection seismology in these kind of questions.
Greg, and then Jerry.
I see your volcanic eruption index follows a power law. Now, the question is, these eruptions, the number that fall into each category is on a continuum from many small ones to a few large ones, or are they like bimodal, the small ones and very big ones?
No, there's
an upper limit to the largest eruption you can get off.
Yeah, so that's an interesting question. I mean, obviously the number of, I'm going the wrong way. The number of small ones is much larger than the biggest ones, but the total volume that's erupted in these matches, an integrated volume over a period of time from these ones here. But it just takes longer to build something like this. And as we just said, you can only do it in certain types of tectonic environment. There's a spectrum of sizes. There's a step function between the frequency of VEI 6 to 7, and then another step function to VEI 8, because it just seems to take inordinately longer to produce these really big ones here. So, the periodicity of these is of the order of hundreds of thousands of years, this of the order of thousands of years, centuries, and so on. But that's, averaged over what we know.
Okay, last one from Jeremy, then I'll.
Thank you for the presentation.
Thank you.
I see that the altiplano is having a very high elevation, which is much bigger than the system we consider. Can you comment on your view? Why is there a high elevation of the altiplano, and how does it compare with the magmatic system?
Sorry, compared with?
The magmatic system you are looking at, compared to the high elevation of the altiplano, which is actually bigger, I think, than the.
Yeah, so if you take the entire Central Andes, about 3/4 of that is made up of the Altiplano Puna. All of the Central Andes is part of that silicic plateau. So there is silicic volcanism throughout the entire length of the Central Andes. So I would say that there is a silicic batholith pretty much underneath the entire length of the Central Andes, and the tops of that are around 2 kilometers or so. So if you think about the contribution of that buoyancy to the elevation, I think it's a significant contribution of some of that elevation is from the magmatism, but the rest is all due to tectonics, the doubling of the thickness of the crust.
In the orogenic research, there is the idea that you have this buoyant lower crust, which is made of hematite that can sustain the height of the magmatic integrated.
Yeah, so here, here the buoyancy is driven by the upper crustal plutonic system, in my view.
Okay, let me end this with one comment I want to make, and that is that for so many decades I have felt that those of us who study old rocks, and a lot of us live around here because there's plenty of old rocks in southern Africa, have a great deal to learn from a guy like him who studies modern active processes, and we need to talk to each other more. So I'm very grateful for the lecture, which I thought was great. And so, for example, I think tomorrow Sean will be taken by Ben and Sue to look at the bush vents, where there are the Greenberg Gimbrites and whatever the hell they are, and he can teach us something about these kind of processes from his experience with active. So we need to do more of this, I think. Anyway, thank you so much, Sean.
Thank you for the invitation. Thank you.